Welcome to the Deep Dive, the show that's your shortcut to being truly well-informed, transforming complex sources into essential insights. Today, we're plunging into what's really the bedrock of organic chemistry, nucleophilic substitution at saturated carbon. Our journey takes us deep into Chapter 15 of, well, a classic text, Organic Chemistry, second edition by Clayden, Greeves, and Warren. If you're an upper-level undergraduate aiming to really master mechanistic reasoning, reaction pathways, functional group transformations, stereochemistry, and maybe even the retrosynthetic side for SN1 and SN2 reactions, well, this deep dive is absolutely for you. Okay, let's unpack this.
Yeah, these reactions, they're not just something you memorize for an exam. They are, the fundamental language for understanding just countless transformations in organic synthesis.
Yeah.
It's really not enough to know what happens. True mastery comes from understanding how these reactions unfold, at the molecular level, that mechanistic insight. That's your ultimate predictive tool.
It's fascinating how different seemingly similar reactions can be. We've seen substitutions before, haven't we? Like nucleophiles attacking those trigonal sp2 hybridized carbonyl carbons. The nucleophile adds, then something leaves.
Exactly.
But how is substitution at a tetrahedral sp3 or, saturated carbon atom fundamentally different from that? What makes it such a unique puzzle?
That really is the crux of it. With a carbonyl, you got that pi bond. The nucleophile can sort of add to it first, pushing electrons onto the oxygen. Easy pathway.
Okay.
But in a saturated carbon, no pi bond.
Mm-hmm.
There's no empty orbital just waiting there for an addition. A direct attack like that, it would force carbon to become 5-valent.
Which it just doesn't do.
It just doesn't do that. It's physically impossible, basically. And that absolute constraint forces two entirely new, quite distinct mechanisms to emerge.
And these are the famous SN1 and SN2 mechanisms. So if carbon can't be 5-valent, what exactly is happening? And what do these mechanisms mean for us practically, in the lab?
Precisely. Understanding which mechanism is at play tells you pretty much everything. What conditions will give you the best yield, whether you need a really strong nucleophile or maybe a specific solvent, and crucially, what the stereochemical outcome will be. It's all about choosing the right molecular tools for your synthetic goal.
Okay, let's start with SN2 then, what I sometimes think of as that beautifully choreographed, concerted dance.
That's a great way to put it, actually. SN2, standing for substitution, nucleophilic. Second order, it's a single, perfectly synchronized step.
Wow.
No intermediate hanging around. The nucleophile attacks as the leaving group departs. Think about hydroxide reacting with N-butyl bromide to form N-butanol. It's just this seamless transition. And the kinetic evidence for this, work pioneered by Hughes and Ingold way back in the 1930s, reveals a really crucial detail. SN2 reactions are second order.
Second order.
For an upper-level chemist, this means the rate directly depends on the concentration of both the alkyl halide and the nucleophile. Double either one. You double the rate. It's a direct proportional relationship. That's immediate practical information right there.
Okay, here's where it gets really interesting then. Knowing the rate depends on both reactants. How do we actually manipulate the reaction conditions to our advantage? What factors give us control over SN2?
It really boils down to three key players: the nucleophile itself, the carbon skeleton it's attacking, and of course the leaving group. First, the nucleophile. Its strength is paramount.
Right.
When the attacking atom is the same, say, you're comparing different oxygen nucleophiles like hydroxide versus water nucleophilicity, generally parallels basicity. Stronger bases, being less stable as anions, are just more eager to react. So if you want a fast SN2, choose a strong nucleophile, like hydroxide. Then there's the carbon skeleton, and this is all about steric hindrance. Crowding, SN2 reactions go fastest with methyl groups, then primary alcohol leads. Secondary carbons, they react slowly. And tertiary carbons, well, they typically don't react by SN2 at all.
Just too crowded.
Exactly. The nucleophile physically can't get to the reaction center. It's blocked by those bulky alkyl groups. It's like trying to navigate a really crowded room. You just can't get through easily. And finally, the leaving group. This is critical for any substitution, SN1 or SN2. A good leaving group has to depart as a stable weakly basic anion, and the carbon-leaving group bond should be relatively weak. For the halides, iodide is by far the best.
Okay.
Then bromide, then chloride, and fluoride is actually very poor. This links directly to the stability of the resulting anion and the CX bond strength.
So we've covered the kinetics and what influences the rate, but what does this concerted dance actually look like at the atomic level, especially thinking about stereochemistry? What's happening in that transition state?
Okay, so in the SN2 transition state, the nucleophile attacks the carbon from the side opposite to the leaving group, 180 degrees away.
Backside attack.
Backside attack, exactly. As the new bond forms and the old bond breaks, that central carbon becomes transiently 5-coordinate, sort of like a trigonal bipyramid.
Yeah.
Imagine the central carbon with 3 groups flat in a plane, and the incoming nucleophile and departing leaving group are positioned above and below that plane.
Right.
This simultaneous attack and departure forces an inversion of configuration at that carbon center. The classic analogy is an umbrella turning inside out in a high wind. If your starting material is chiral, your product will have the opposite configuration, guaranteed. And this inversion is actually a really powerful tool in synthesis. We see it when making ethers from alkoxides and methyl halides, for instance. Even faster reactions happen with alpha-halocarbonyl compounds. That adjacent carbonyl group helps stabilize the transition state, making them incredibly reactive toward SN2.
Okay. And what about the solvent? What role does it play in this, tightly coordinated process?
Right, solvent. SN2 reactions generally prefer aprotic, less polar solvents, things like acetone, DMF, or DMSO.
Why is that?
Well, these solvents are polar enough to dissolve the ionic reactants. But crucially, they don't strongly solvate or cage the anionic nucleophile with hydrogen bonds. This leaves the nucleophile kind of naked and much more reactive. A solvated nucleophile is sluggish, an unsolvated one is like a sprint runner ready to go. Now let's pivot to the other side of the coin, the SN1 mechanism, the stepwise journey. This pathway is fundamentally different from SN2 because it's a two-step process. First, the leaving group just departs on its own.
All by itself.
All by itself, forms a carbocation intermediate. Only then does nucleophile attack that highly reactive electron-deficient carbocation. And the kinetic evidence for SN1 reactions, again thanks to Hughes and Ingold, shows they are first order. And here's a massive distinction. The rate depends only on the concentration of the alkyl halide.
Not the nucleophile at all.
Not the nucleophile at all. Its concentration doesn't even appear in the rate equation. Rate equals K1 times the alkyl halide concentration. That's it.
So the nucleophile is just hanging out, waiting for its turn. That's fascinating. If adding more nucleophile doesn't speed things up, what does dictate the rate for SN1?
The core insight here is that the formation of that carbocation, that's the slow step, the rate-determining step. It's the bottleneck.
Okay.
So what affects that bottleneck? It's all about the stability of the carbocation intermediate itself. Carbocations are electron-deficient, positively charged, and planar sp2 hybridized with an empty p orbital. The more stable that carbocation, the lower the energy barrier to form it, and therefore the faster the SN1 reaction. And alkyl substituents stabilize carbocations through something called hyperconjugation. It's a subtle donation of electron density from adjacent CH or CC sigma bonds into that empty p orbital. It helps spread out the positive charge.
All right.
This is why tertiary carbocations are the most stable, then secondary. Primary and methyl carbocations, highly unstable in solution, usually don't form readily via SN1. Our understanding of these fleeting intermediates really leaped forward thanks to George Ola's Nobel Prize-winning work in 1994. He used these specialized non-nucleophilic environments, like liquid sulfur dioxide at very low temperatures.
Superacid conditions.
Exactly, superacid conditions. And he was able to actually observe stable carbocations, like the T-butylcation, using NMR spectroscopy. Seeing them directly provided just irrefutable proof of their existence and their planar structure. But stabilization isn't just about alkyl groups. Carbocations can also be powerfully stabilized by resonance. Think allylic and benzylic systems, where the positive charge gets delocalized over multiple atoms through pi bonds.
Makes sense.
Even more dramatic stabilization comes from an adjacent lone pair on a heteroatom, like oxygen or nitrogen. This forms highly stable species like oxonium or aminium ions. Methyl-chlormethyl ether, for example, reacts rapidly by SN1 because that adjacent oxygen's lone pair dramatically stabilizes the intermediate carbocation. And here's another interesting twist. Steric effects. Remember how they hinder SN2?
Yeah, crowding is bad for SN2.
Well, for SN1, they actually accelerate the reaction. As the carbon goes from tetrahedral in the starting material to a more open, planar carbocation-like transition state, larger alkyl groups can spread out more easily. This reduces steric strain and actually stabilizes the transition state, speeding up that first rate-determining step.
Okay, that's counterintuitive, but makes sense with the geometry change. So SN2 gives us inversion of configuration. What about SN1? How does it affect stereochemistry, especially if we start with a chiral molecule?
This is a major, major contrast. Because the carbocation intermediate is planar, essentially flat like a disk, the incoming nucleophile can attack from either face, top, or bottom with roughly equal probability.
Ah, 50-50 chance.
Pretty much. This leads to residuization. You end up producing an approximately 50.50 new mixture of enantiomers if the starting material was optically active. So if you begin with a pure enantiomer, SN1 will generally give you a racemic mixture as the product.
And for solvents, if SN2 likes those naked nucleophiles in a product's solvents, does SN1 demand a completely different kind of solvent environment to stabilize those highly charged intermediates?
Absolutely. Polar product solvents are the friends of SN1. Think water, formic acid, alcohols. These solvents are excellent at stabilizing the developing ions, both the negatively charged leaving group and the positively charged carbocation intermediate. They also stabilize the highly charged transition state, leading to their formation. This strong solvation drastically lowers the energy barrier for that rate-determining step, making the reaction feasible. So now that we've seen both mechanisms, let's just quickly compare them side by side. Structurally, it's a really useful guiding principle for synthesis. Methyl and primary alkyl halides generally prefer SN2. Tertiary alkyl halides strongly favor SN1.
And secondary are the tricky ones.
Secondaries are the wild cards, yeah. They can often go by either pathway, and it really depends on the specific conditions you choose, the nucleophile, the solvent, etc. But remember those important exceptions. Allelic and benzylic halides are good for both SN1 and SN2 because of resonance stabilization. Alpha-alkoxy groups push towards SN1 because they stabilize the carbocation, but alpha-carbonyl groups, they actually disfavor SN1 because the carbonyl is electron withdrawing, and they tend to push towards SN2.
Right.
And those notoriously hindered neopentyl halides, sterically crowded near the reaction center. They typically avoid SN1 and react very, very slowly by SN2. Stereochemically, the takeaway is crystal clear. SN2 gives inversion. SN1 leads to racemization.
Got it.
And solvent effects are basically diametrically opposed. SN2 thrives in polar product solvents. SN1 demands polar product solvents. You know, the quantitative data from Clayden's book really drives this home. There's a graph showing relative rates on a log scale. For SN1, going from methyl to primary, secondary, and then tertiary, the reaction rate can skyrocket by factors of millions, even billions. For SN2, it's the complete opposite trend. Methyl is fastest, primary is okay, secondary is slow, and tertiary is practically non-existent. This stark difference is precisely why understanding these mechanisms is so critical for predicting reaction outcomes. Electronic effects also play a huge role, especially in systems like benzylic halides. Electron-donating groups on the ring, like a methoxy group, dramatically accelerate SN1 by stabilizing that positive charge in the carbocation. Conversely, electron-withdrawing groups, like a nitro group, strongly disfavor SN1 because they destabilize positive charge. They'll push the reaction towards an SN2 pathway if that's possible.
This all ties directly into designing reactions then. So if I'm trying to actually make something specific in the lab, how do these rules about SN1 and SN2 become my practical guide? Let's talk a bit more about the reagents themselves, focusing on the leaving groups and the nucleophile.
Okay, yeah. The leaving group is absolutely paramount for both SN1 and SN2. Why? Because its departure is always part of the rate-determining step, whether it leaves first SN1 or simultaneously with attack, SN2. So a good leaving group must be able to depart as a stable, weakly, basic anion. And the carbon-leaving group bond should be relatively weak. As we mentioned, iodide is excellent, large, polarizable, and the iodide anion is very stable. It's the conjugate base of a strong acid, HI. Now here's a really common challenge you face in functional group transformations. Alcohols. Their hydroxyl H group is, well, notoriously poor as a leaving group.
Why is that again?
Because the hydroxide ion is a strong base and a pretty unstable anion on its own. It simply won't leave easily. So the question becomes, how do we make an OH group leave? One way, often used for tertiary alcohols and SN1 reactions, is to protonate the hydroxyl group with a strong acid. This converts it into OH2 plus a chain, essentially a water molecule waiting to depart. And water H2O is an excellent leaving group.
Okay, protonate it. What else?
For SN2 reactions with primary alcohols, you might use specific phosphorus regions like PBr3 or PCl3. These convert the OH into a good leaving group in situ. But probably the most versatile and widely used method across the board is to convert the alcohol into a sulfonate ester, things like tosylates, TSO, or mesylates, MSO. Oh, tosylates and mesylates, hear those a lot. You do, because they're great. Sulfonate anions are exceptionally stable because that negative charge gets delocalized over 3 oxygen atoms through resonance. This makes them superb leaving groups, often even better than halides. They allow even relatively weak nucleophiles to participate effectively in SN2 reactions. And if you need a really reliable way to replace an OH group with a nucleophile with inversion of configuration all in one pot, the Mitsunobu reaction is often the go-to answer. It's a clever multi-reagent system using things like triphenylphosphine and DED. It looks complex, but it effectively activates the OH and facilitates an immediate SN2 displacement, giving you that clean inversion. Powerful tool for stereo control.
Okay, so we can make alcohols reactive. Beyond the common alkyl halides and activated alcohols, what other electrophiles are frequently seen in these kinds of substitution reactions?
Well, ethers are generally quite stable, very unreactive usually, because the alkoxide anion, RO, is a poor leaving group, similar to hydroxide. To make ethers react via substitution, you typically need to protonate the oxygen with a very strong acid or use a powerful Lewis acid like boron tribromide, BBr3, to basically make the leaving group better before a nucleophile can attack.
So they need some persuasion.
They definitely need persuasion.
Ye-
Epoxides, however, are a fascinating exception. These are strained, three-membered cyclic ethers.
Right, the triangular ones.
Exactly. They are primed for SN2 attack because of that immense ring strain. Opening the ring relieves that strain, which is energetically favorable. And because it's typically an SN2 process, it proceeds with inversion of configuration at the carbon being attacked. This happens even without needing a strong acid, although acid can catalyze it. It's a very useful reaction for making things like 12,2-diols with specific stereochemistry.
Okay, now let's flip back to the nucleophile and its specific role. For SN1 reactions, remember, nucleophile strength doesn't affect the rate. It's not in the rate-determining step.
Right, it just waits for the carbocation. Exactly. This means even very poor nucleophiles can successfully react if the carbocation is stable enough. The Ritter reaction is a fantastic example. It forms a CN bond to a tertiary center using a nitrile, which is a notoriously weak nucleophile in the presence of strong acid. It works because the stable tertiary carbocation forms first and is just waiting for anything to attack it. For SN2 reactions, however, a good nucleophile is absolutely essential. Its concentration and its reactivity matter. Nitrogen nucleophiles, like simple amines, are decent nucleophiles, but they often cause a practical problem, overalkylation.
Reacting more than once.
Yes, the primary amine product is often still nucleophilic enough to react again with the alkyl halide, leading to secondary amines, then tertiary amines, even quaternary ammonium salts. You get a messy mixture. A really clever retrostatic trick to avoid this is using the azide ion.
N3.
Azide N3-. Right. Azide's a good nucleophile, but crucially, once it reacts with an alkyl halide to form an alkylazide, RN3, that product is generally non-nucleophilic, so the reaction stops cleanly after one substitution. Then you can easily reduce the alkylazide, say with lithium aluminum hydride or catalytic hydrogenation, to get the desired primary amine without overalkylation problems. Very neat strategy. Sulfur nucleophiles, like thiolate anions, RS, are also excellent SN2 nucleophiles. Interestingly, they're often even better than their oxygen analogs, like alkoxides, RO, despite sulfur being less electronegative and thiols being less basic than alcohols.
That seems counterintuitive again. If it's less basic, why is it a better nucleophile?
This highlights a critical nuance in nucleophilicity trends. Here's a key takeaway. When the attacking atom is the same element, like comparing hydroxide HO and phenoxide PHO, then nucleophilicity generally parallels basicity. The stronger base is usually the better nucleophile. But when the attacking atom is different, especially going down a group in the periodic table, like oxygen versus sulfur, or fluorine versus chlorine versus bromine versus iodide, then orbital interactions, specifically homo-LUMO interactions, tend to dominate over simple basicity or electrostatics.
Homo-LUMO.
Yeah, the highest occupied molecular orbital of the nucleophile interacting with the lowest unoccupied molecular orbital of the electrophile, which in SN2 is the sigma antibonding orbital of the CX bond. Larger atoms lower down the periodic table, like sulfur or iodine, have higher energy, more diffuse homos. Their valence electrons are further from the nucleus and less tightly held. These higher energy orbitals provide better energy match and overlap with the CX sigma LUMO low.
Better overlap means faster reaction.
Better overlap means a lower energy transition state and thus faster reaction. This is why iodide I is a much better SN2 nucleophile than fluoride. F and thiolate RS is better than alkoxide, RO, even though F and RO are much stronger bases. This leads nicely into the concept of hard and soft nucleophiles. It's a useful qualitative idea. Hard nucleophiles are typically small, highly charged, not very polarizable, and often strong bases like hydroxide or fluoride. They tend to be attracted electrostatically to hard electrophilic centers, which are also small and highly charged, like the carbon of a carbonyl group.
Okay, yeah, like hard.
Pretty much. Soft nucleophiles, on the other hand, are typically larger, more polarizable, often less basic, and have higher energy homos like iodide or thiolate or triphenylphosphine. They prefer to react with soft electrophilic centers, which are larger, less charged, and more polarizable, like a saturated carbon atom undergoing SN2 displacement. The reaction is driven more by good orbital overlap than just charge attraction.
So SN2 reactions typically involve soft nucleophiles attacking soft electrophiles.
That's a good generalization, yes. And here's a neat synthetic trick that ties things together. Some of the best soft nucleophiles, like iodide, are also excellent leaving groups in SN2 reactions because the iodide anion is so stable.
Ah, I can play both roles.
Exactly. This dual role can be incredibly useful. For instance, sometimes you want to react an alkyl chloride or bromide with a relatively weak nucleophile, and the reaction is slow. You can add a catalytic amount of sodium iodide. The iodide, being a great nucleophile, rapidly displaces the chloride or bromide via SN2. Then the resulting alkyl iodide is much more reactive towards your desired weaker nucleophile. The iodide acts as a nucleophile, then gets kicked out as a leaving group, constantly regenerating itself to catalyze and speed up the overall transformation. It's called nucleophilic catalysis.
What a journey. Seriously, from those fundamental differences in reaction centers sp2 versus sp3 to the intricate dance of kinetics, stereochemistry, solvent effects, and reagent choice. It's really clear that understanding the nuances between SN1 and SN2 mechanisms isn't just, academic. It provides profound predictive capability for actually designing and executing organic syntheses in the real world. We've truly unpacked the core of Chapter 15 from Clayden, Greeves, and Warren today.
Absolutely. And, while SN1 and SN2 provide this powerful foundation, it's worth remembering, especially with SN1, that carbocations are highly reactive intermediates. They have more surprises up their sleeve.
Yeah.
They don't only get attacked by nucleophiles.
Wow. What else can they do?
Well, they can also undergo other transformations. Sometimes the initial carbocation can actually rearrange maybe a hydrogen or an alkyl group, shifts over to form a more stable carbocation before the nucleophile attacks. This can lead to unexpected skeletal structures in the product.
Wow. Okay.
And they can also undergo elimination reactions, losing a proton from an adjacent carbon to form an alkene, often competing with substitution. This really raises an important question for synthesis. When you generate a reactive intermediate like a carbocation, what other pathways, perhaps unintended ones like rearrangement or elimination, might it follow, and how can you control that outcome?
Fascinating. The complexities of carbocations clearly open up a whole new world of reactivity, rearrangements, eliminations. Sounds like material for a future deep dive, perhaps. Thank you for walking us through all this today, and thank you, our listener, for being part of this deep dive into nucleophilic substitution. Thank you for being part of the Last Minute Lecture family. Keep diving deep.